Michael has been interested in astronomy since about the age of 5, even though his degree is in linguistics and especially variable stars. He independently discovered Nova Cygni in 1975 while doing his A-levels and being a member of the American Association of Variable Star Observers, an amateur professional body affiliated to Harvard University. His special interest is in young variable stars, and he runs the Young Stellar Objects section at the American Association of Variable Star Observers. In 2002, he was awarded a NASA grant to participate in an astrophysics conference on the Big Island of Hawaii, and has written a book on astronomy with binoculars. So please welcome tonight, Michael. Thank you.
Oh, thanks very much.
Okay, Michael.
Right, why do we do variable stars? Well, obviously, first we sort of need to know what a variable star is, and obviously they're stars that change their brightness. Really good example of that probably everyone knows is Betelgeuse, or however you want to pronounce it, the big red one in Orion. That's a really famous variable star, and it's obviously been in the news a bit. The other really good thing about variable stars is any amateur astronomer can look at them. As was mentioned earlier, I've written a book about astronomy with binoculars. You can see hundreds of variable stars with a perfectly ordinary pair of binoculars. So you don't need to spend lots and lots of money on expensive telescopes or imaging equipment or anything like that. Just a perfectly ordinary pair of binoculars. And the other really great thing is your observations will have value to astronomy and astrophysics. There are just too many examples of this to mention. They're just all over the literature, and there are lots of them. Even in the older variable star catalogues, there are about 25,000. And what we now call VSX, which is Variable Star Index, which is actually hosted at the AVSO, it now contains over 1 million variable stars. Some of those variable stars are only just variable. I really want to concentrate tonight on the sorts of variable stars that amateurs can look at, and for which you don't need expensive equipment. So this is at the bottom end, really. There's not too much in the way of jargon involved here, but the main sort of jargon word, really, in the world of variable stars is the light curve. Basically, a light curve is just a graph which shows you how the star has been changing its brightness. And here we've got a light curve of this is a pulsating variable. I'll explain sort of a little bit later what they are. Sorry, there we go. As you can see, the brightness keeps changing over time. This is a very long period because it's been set up to show how the period of this star, the period is just the time from one maximum up here to the next one. In this case, it's about 300 days. But recently, since about fairly recently, on an astronomical scale, since about the middle of the 1970s, the period has been changing. And as you can see, as we come up today here, it's kind of lost all sense of any period whatsoever. So this really is kind of the evolution of a star over even a part of a human lifetime. So normally people associate stellar evolution with millions and millions and even billions of years, but here you can see things changing on a much faster level. Right, so I mean, that is basically light curve, and from the shape of the light curve you can get some idea as to what sort of variable star you're dealing with, because there are lots of different types. Right, just going to have a look at another type here. This is a star that spends most of its time in its bright state at maximum. And roughly once a year, it plunges from sort of magnitude 12 down to about magnitude 14 or 15. I'll explain a little bit about this particular star, a little bit. But again, all these observations that you can see here, each dot is a single observation almost entirely, I believe, by amateur astronomers, quite a lot of them by me, quite a lot of them by Gary Poyner, who you've probably heard of, who runs the BAA variable star section, I think. Well, he's certainly very active in it anyway. These are all amateur observations of this star. So that's the only record we've got of what's going on. And what is going on there is pretty strange. Okay, so this is a star that probably quite a lot of people have heard of. It's Algol. Algol is what we call an eclipsing binary. It's made up of two stars, one quite a bit brighter than the other. So as the two stars revolve around each other, here we're at the normal phase, we're getting the light from sort of both of the stars at the same time, so it's maximum light. And here, as you can see, the bright one has gone beyond the darker one, so more light's being cut off, therefore the system is faded. And again, as the bright star now emerges, we come back to maximum again. And now we have a reversal, so the bright one is in front of the dim one, so there is still a dimming, but not very much, okay, because the light of the bright star isn't being cut off. And round we go again, and this period here is very accurately known, because obviously the two stars are revolving around each other in the same period of time. So this period here is perfectly regular. Most of the variable stars amateurs tend to look at are not regular, because they're then more exciting. You don't always know what's going to happen next, and that's a sort of interesting bit. There are a whole class of pulsating stars. These are old stars, quite near the ends of their lives, and the nuclear reactions in the middle of in the sort of centres, the core of the stars, are getting a bit weaker because it's running out of fuel. So then you have a kind of a fight between the outward urge, if you like, of the radiation, of the multi-million degrees right at the core of the star, and then you have the other force of gravity, which tends to contract the star. Therefore, they tend to pulsate. And there are a whole group of these stars. As I said, they're all oldish stars, but they're certainly all older than the sun. And one day the sun will probably be doing something very similar to this. The really regular ones, again, this is probably something you've heard of, we call Cepheid variables, because the first star of the type to be discovered was Delta Cephei, which also happens to be a binocular double star, and it's really worth looking at because it's sort of yellow and blue colour, a little bit like Albirio. But yes, and again, this variation here is perfectly regular from sort of from one phase to the next. So again, amateurs tend not to observe Cepheid variables other than for sort of practice, if you like, when you're first starting off, because you know that you're looking at a variable star and that star's light's going to change. That's why they're good for practice. But once you start getting into it, you tend to want to look at the ones that maybe give you a bit of a surprise. And these are the ones that we're talking about here. These we call Mira stars. Again, because the first star of that type to be discovered was Mira, Omicron Ceti. Now here, the variations are not nearly so regular. As you can see here, this kind of one is slightly different to that one. The rise here is a bit quicker, and the minimum's a bit fainter. And as the period, this is about 330 days, I think, with Mira. That's from one maximum to the next. It's about 330 days. You only really need to observe these stars about once a month, I suppose. Sometimes twice a month, if they vary a bit quicker, like this one, which is X Camelopardalis, which in this case the period from one maximum to the next is about 150 days. So it's it's less than half of the Mira. So you'd probably want to observe that about twice a month. As we go towards the sort of quicker stars, they tend to become a little bit more irregular. This kind of maximum here has a little stop on it, and this one doesn't. And all sorts of stuff going on really. Can we have another star in Camelopardalis, which it's a really good constellation for variable stars, Camelopardalis. Not many people know about it. It's, you know, it's not one of the most famous constellations, but it's really good if you're a variable star observer. There are a whole host of these stars. Betelgeuse is one, for example. But it doesn't really have a period. It's what we call an irregular red variable. There are lots of other irregular variables which have nothing to do with this. It's slightly confusing, but these are basically all sort of yellow, orange, and red stars. All right, they tend to be a bit more massive than the Sun. In some cases, such as Betelgeuse, you know, quite a lot more massive than the Sun, which means that it might go supernova, which is what all the interest has been about. Now here we have some more irregular variables, but as you can see, the light curves, if you remember what the light curve of Algol was like, starting off bright and then fading and then coming back again, this is kind of Algol in reverse. These stars spend most of their time at minimum, which in the case of SS Cygni, which is the most famous one, is about magnitude 12, so you need quite a small telescope will show it, even at minimum. And about once every 30 or 40 days, it will shoot up to about magnitude 8. Sometimes in the course of a night, really, more or less. And it does all sorts of interesting stuff, as you can see here. It's come back down to minimum, and it's going to rise to maximum, but it doesn't quite get there, and then it falls again, then it rises again. All sorts of fun going on here. And again, virtually all of these observations that have been made to actually form this light curve here are all by amateur astronomers using small telescopes. A slight subclass of this type, which we call dwarf novae, because they are basically novae on a small scale, hence the name. There's a kind of a subclass of these which are called Z Camelopardalis stars. Again, Camelopardalis, you see. They tend to do the same thing, and then complete without warning, they'll completely stop varying at all. And in fact, ZCAM itself, at the moment, is in one of these standstills, as they're called. We don't know when it's going to end. It could end tomorrow night, it could end in 3 or 4 months' time. And obviously, these stars have to be monitored because there's still a lot about them in sort of astrophysical terms that we don't understand. So the more observations we can get, the more we will tend to understand them. ZCAM is a pretty bright member of the class. I mean, at minimum, it's about magnitude 13.5. So, you know, you need a slightly bigger telescope. But at maximum up here, it can be about magnitude 10.5. So it's usually visible in a small telescope at some stage, and the standstills, the interesting bits, normally take place at about magnitude 11.5 in this particular star. This is the brightest one, most of them are a little bit fainter. Right, now these are the sort of stars I showed. These are all very young stars. They are still, some of them, in the process of contracting out the gas clouds, which is where all stars are made. Stars are made basically they're made in nebulae. And here we've got two particularly interesting stars. The top one, as you can see from the magnitudes here, this is entirely visible in binoculars at all times. So even if you don't have a telescope, you can follow this interesting star. As you see, it exhibits lots and lots of variations. And the other interesting thing about it is it's actually a double star. And SU Aurigae here is its companion. So you can actually look at both of these stars at the same time. A very small telescope will show both of them. So say you can see this one in binoculars, but even if you've got your sort of classic old-fashioned sort of 6-inch reflector or whatever, that's quite suitable for this. Because they're still interacting with the nebular material that they've actually formed from, the variations can be unpredictable, sometimes violent. And here's a particularly good example of a completely unpredictable star, RR Taurei. Actually, this probably shows one of its more sort of leisurely examples. It normally actually varies more than this, but as you can see from here, there's no period at all. It's not like the Cepheid variables or all the eclipsing binaries, that you can practically set your watch by. This changes again. This changes over the course of a night, and actually not very far in the sky from this star is another star called Taurei of the same type, and I've actually watched that brighten in front of my eyes actually as I look at it. So this is real instant bang for your buck. The last one I want to show here is V730 Cephei. Now, as Sean will tell you, Cepheus is the best constellation in the sky, and I agree. There are lots and lots of nebulae in it, which are very, very pretty. But the nebulae are, as I said earlier, also the place where stars get made. So there are lots of these young, very, very irregular variable stars here. In fact, when the star was discovered, it was so new it didn't even have a variable star name like V730 Cephei. It was just a name in some catalogue. It was just called MISV 1147. That really rolls off the tongue, doesn't it? But it now has a proper variable star name, V730 Cephei. Now it's quite a bit fainter, as you can see. It goes between magnitude 13 and about 16. And I know that because if you look at this little data point down here, that's my observation at 15.7, which is I think it's the faintest minimum ever recorded for that particular star. So that was a really useful observation. But the other strange thing about it is, the following day, a friend of mine, Mike Simonson in America, was also looking at this star, and he made it magnitude 14.2, basically on the same day. And why this star shows very, very deep minima, as you can see here, is we think what's happening is it's forming a system of planets, and the clumps that will eventually, get bigger and bigger and form planets, just like the Earth, are so arranged that the clumps pass between the star and us. So it seems to cut off the star's light, which is very similar to what we get in the case of the eclipsing binaries like Algol that we saw at the start. But here, of course, the effect is the same, but the cause is totally different. And again, it's not regular, but it varies, as you can see here. It varies very, very violently. And obviously, if we have stars forming out of nebulae, we have nebulae. So we're going to see some pretty pictures now. All right, this is a lot of you will know this. This is called the Elephant's Trunk Nebula, IC 1396. And in this dark bit here, the dark nebulae are the interesting bits because they're made out of cold gas, which is why they're not shining, which is why they're being dark. You can see lots of them here. And all the cold gas there is the stuff that the stars are going to be formed out of. And in fact, in this very small area here, the Spitzer Space Telescope, which observes, I think, in X-rays, has detected about 300 forming stars, which you can't see. And that's because the gas here, okay, it looks dark, but it's so dense, okay, it's a very, very large area. And whilst there isn't comparatively too much material there, the area is so large that in absolute terms, yes, there is a lot of material, so that's where all these stars are forming from. And you can see in other various areas here, there are nice, interesting little dark nebulae. In fact, I think this might be one of Sean's pictures. So if I just click on that, we'll see another nebula. Now, some of you might know what this is. This is Hubble's Variable Nebula in Monoceros. I can't remember the NGC number at the moment. But this is a nebula, and this is R Monotorotus, which is a variable star right at the tip of the nebula. And there are quite a few nebulae that actually look like this, basically sort of triangular, with the star at the tip. And we'll see in a moment why there are so many stars that actually look that way. Right, why they look that way is because when a star forms, it's got all the gas swirling around it, and eventually this gas will collect, and it will essentially form what will be the equator of the star, and that's sort of dark piece here. that will be the equator of our sort of future star. You can't really see the star properly because it's behind all this gas, which is going to go on to form planets, or at least some of it is, because we're now sort of 99.99% sure that all stars have planets, simply because star formation makes planet formation. Planet formation is a byproduct of star formation. So we think that virtually all stars have, or at least start off with planets. Sorry, I better just go back there. But the really interesting bits is the green stuff coming out. Now these will be the poles. And the reason why stuff is coming out of the poles is if you think of a bath filling up with water, oh sorry, I keep clicking on that, I don't mean to. Eventually the bath is going to overflow, and this is the overflow from the star. We call this a bipolar outflow. For obvious reasons, there's material coming out from both poles. And the interesting thing about this material is it's being emitted at a fair old rate of knots. And the reason why it's coming out of the poles is because all of the material is coming in to the equator. So the material that the star's made of has to go somewhere. It's a bit like our sort of filling up bath, and instead of going through the overflow plug, it goes out through the poles, because they're the points of least resistance. Because all the gravity is coming in this way, so it can't escape the way that the stuff is coming in. So, you know, as I say, it takes the path of least resistance and it goes out through the poles. Now, all this material can then go on to cause more star formation nearby. So it's a continuous kind of sort of fractal process, in fact. But of course, the actual shape that these systems give you depends on the angle that we're looking at it. Here we've got a lovely one. It's almost a kind of sort of a butterfly effect. Here's another one, which is a bit faint, but on long-exposure photographs, in fact, what you can see is you can see a very, very faint kind of mirror image of that one. Because what's happening here is the bipolar outflow is pointing very slightly towards us of this particular pole. So obviously the other pole is kind of pointing away, which is really why it's fainter. And that's what we've got with our monocerotis. Here's one of the bipolar outflows. We can't see the other one because the star's in the way. But these outflows are very common, and they're called Herbig-Haro objects, or just HH objects for short. Okay, so there we have some of them. And here's another one that some of you might know, the Propeller Nebula. Now here we've probably got a bipolar outflow as well, but as you can see, it's not straight. And we think what's happening here is, again, you can't see anything in the middle because, you know, that's the equator of the star, and the gas is kind of getting in the way. But we think what's happening here is, okay, you would normally have a bipolar outflow going sort of like that and like that, but we think there's an intervening star probably behind this cloud, which is distorting each of them into this sort of propeller shape. That's very, yeah, I mean, it's obviously a beautiful thing to sort of photograph as well. Right, I don't actually want you to read this because some of it is a little bit sort of abstruse, but the main point of this is the sort of question marks, because this gives you some idea of all the stuff that we don't know. All right, because science really flourishes on the stuff that we don't know. It doesn't necessarily flourish on the stuff we do know. The interesting stuff is the stuff that we don't know or we're not sure of. So, you know, this is really just for the question marks. Okay, so this is a very, very brief sort of view of certain kinds of variable stars. Now, then we're just going to have a look about how you actually do it. So there we are. Really, the first step is learning to recognise what various magnitudes look like, because how variable star observing works is you pick stars that you know aren't variable and whose magnitude you know, and you compare the variable star with those ones. So you know, it's a little bit sort of pushing around to start with, but as you get more used to doing it, you will get more accurate in your observations. And a really good place to start to look at what magnitudes look like is our old favourite of sigmas. So here are the magnitudes of the sort of middle stars of the cross, if you like. So the practice starts with first look at a gamma and then maybe look at epsilon here and say, oh yes, I can see a bit of difference between those two. That one's a little bit fainter. So in that case, you've learned to recognise the difference of 0.3 magnitudes. That's the difference between these. And then you can maybe look at the difference between that one and that one. You know, that might appear slightly greater, which it is, because the difference between this one and this one is 0.4 magnitudes. And really, your sort of ultimate aim is to get down to recognising a difference of 0.1 magnitude between two stars, which might sound really, really accurate, but in fact, that's what you're aiming for, and it's not that uncommon to find variable star observers who can do that. In fact, sometimes even more accurately than that. So what you need to do this with is a star chart if you're looking at an actual variable star. And here we have our old friend that I was talking about earlier, SS Cygni, which is one of these stars that erupts. It's very easy to find. Well, comparatively easy to find. It's very near a star 75 Cygni, which itself is worth looking at because it's a beautiful golden coloured star. It's really lovely. This is an inverted view with south at the top, by the way. And SS Cygni is easy to find because it's within this little triangle here. And it's right in the middle of these two stars. And all of these stars are really good, what we call comparison stars. They're the stars I was talking about earlier, whose magnitudes we know, and we know they're not variable stars. Obviously, you can't compare one variable star with another one, for obvious reasons. Now, let's say you were sort of going out tomorrow night, and you looked at the star, and you said, oh, it's reasonably bright. In terms of brightness, you think, oh, it's sort of halfway between this one and this one. Now that's 8.6, and that's 9 points. We don't put the decimal point in just in case anyone confuses it with a faint star. So 86 means it's magnitude 8.6, and this means it's magnitude 9.6. Right. So you've sort of placed the brightness of our variable star here halfway between that one and that one. And as the difference here is a whole magnitude, then obviously it's half a magnitude fainter than this and half a magnitude brighter than that. So on this occasion, its magnitude is 9.1, and you would record that, you know, in an observation book or on software or something like that. Now, I mean, that is basically how it works. It's as straightforward as that. All you need is a little bit of patience and star chart. That's it, really. So, as I say, this is sort of how we do it. This example isn't the same as the one I just gave, but it's a different example, which is good, because they do change. That's why they're called variable stars. So here, this is SS Cygni, because obviously in the sky it doesn't look like a little hollow circle. It just looks like any other star. Variable stars tend not to look sort of very, very different from any other stars. So here we have it. Now, to me, I would say it's slightly brighter than this one here, slightly brighter than 96. Maybe I'd put it about magnitude 9.4, something like that. You can, if you want to, actually do it sort of graphically, which comes in really handy. Because that's a permanent record, and that's also a really good way of doing it. So, you know, it's on this line here between these two, and it's quite a lot closer to this one. You can eventually sort of work out what the magnitude is. Right, now I've just got a couple of little things to finish with, really. Now, this won't make any sense at the moment, because what I was going to do was going to go back to these very irregular nebular variable stars and tell you about one of them. we'll have to go back quite a way. I think it might be the next one. No, it's going to be this one. Right. If we look at SU Aurigae here, as you can see, it's like it's very different from that. They are both young stars, but they vary in completely different ways. This one, where you have fairly gentle variation, so you know there's not all sorts of fun and games going on as we've got with this one. These are fairly sort of gentle variations. We think they might be caused by the stars being heavily spotted, because when a star is first formed, it's rotating very, very quickly, and it's probably going to generate lots of star spots. So we think, because this is reasonably regular here, okay, we're having all sorts of interesting stuff here, but most of the time it's reasonably regular. And the first star that we discovered that varied in this way was T Taurei. So they're called T Taurei stars. And I want you to remember that name. Remember T Taurei. All right, and we'll now come to where I'm going to show you how rock and roll variable stars are. They are literally rock and roll. So, remember that name T Taurei? Well, here we have a rock and roll band, and the name of the band is T Taurei. They named themselves after a variable star. They're Dutch. It's a Dutch rock band, and they're called T Taurei. What about that for Kerbals, eh? So just want to show you a little picture of, this is me at the Keck on the top of Mauna Kea in Hawaii. So, you know, really it's a case of observe variable stars and see the world. This wasn't paid for by NASA, 10 days in Hawaii, all paid for by NASA simply because I observed variable stars. So I'll leave that now. So we can come back. Okay, anyone's got any questions? Fire away. Can you hear me?
Okay, thank you, Michael. What we will do is we will just cancel your spotlight.
Okay.
And go back to gallery view. And there's a lot of information there. I'm hoping there's going to be a lot of questions. So, ladies and gentlemen, as we practiced last week, putting up your hand electronically. So if you have a question, then can you indicate electronically? So Peter Lloyd, can you unmute your microphone?
Yes, thank you, Paul.
Okay, Peter, what's your question?
Well, thank you, Michael. Do I take it you always do your magnitude estimations visually? Do you never do it photographically?
I do absolutely everything visually. Yeah.
Okay. Is there any particular reason for that?
It's what I've always done. I don't have any equipment to do it with by any other method, and I'm just happy to be under the stars. I mean, it is quite sort of romantic, actually. Yeah, you know, I'd rather be out there, you know, kind of use on my own body, if you like, rather than a piece of technology.
Fair enough. Thank you.
Thank you, Peter. And Gary Gothorpe. Gary, can you unmute your
I'm
microphone?
unmuted.
Okay, can we have your question then, please, Gary?
I just wondered if you could explain why Betelgeuse dimmed last year and why it's brightened pretty much back to where it should be.
Yes, I mean, obviously at the time various people are asking about this, and I did point out, well, yeah, it's doing that because it's a variable star. It's what they do. They vary. I mean, why it got excessively faint, that's what we don't know. And in fact, that's where the observations come in handy. One great advantage of visual observing is, well, especially with the brighter stars, and you don't get a lot brighter than Betelgeuse, is you can't actually study them with things like CCDs because they will simply burn, you know, they'll just burn them out. They're too bright. So all the observations that we have of Betelgeuse came from visual observers, and in fact, obviously, naked eye observers didn't even need a telescope. But as to why it faded, we're not really sure. But it's just part of Betelgeuse's sort of range of variations. It has, in fact, been fainter than it was last year on one occasion. But it's been known for a long time that it's a variable star. The variability of Betelgeuse was actually discovered by John Herschel. Obviously the son of Sir William. So its variability has been known for an awfully long time. And the fact that it was red suggested to lots of the Victorian astronomers that all red stars are variable, which is sort of true to some extent, I suppose. I mean, some of them aren't very variable at all. They only vary by about 0.2 of a magnitude or something. But then again, at the other end, you've got stars like Mira and Chi Cygni, which can vary by about sort of 9 or 10 magnitudes. So all of these red stars, stars like Betelgeuse, Mira, and so on, they do need constant watching. But the constant watching doesn't have to be, sort of one night and then the next night and then the next one. They do vary quite sort of slowly. So, yeah, as I was saying earlier, usually with the red stars, one observation a month is usually okay, because don't forget, other people in other parts of the world and other parts of the country will also probably be looking at that star as well, which is why it's useful to have a body like the AAVSO who are worldwide. So, you could have an observer in Japan or South America or Finland or somewhere like that, that can observe a given star when we're clouded out in Britain, which obviously hardly ever happens.
Okay, Gary.
Thank you.
Okay, and a question from me then, Michael. How much effect does atmospheric seeing have on your observations?
It doesn't usually have any effect at all. The main reason is, usually if you're observing a variable star, you want to fit the comparison stars in the same field at the same time, so you can, directly do the comparison. So you tend to use fairly low powers, and therefore, well, this is a bit of a generalisation, obviously. But generally, low powers aren't as affected by seeing as, say, if you were looking at something like Jupiter with a power of 300 or 400 or whatever, there every tiny tremor in the atmosphere is kind of magnified 300 or 400 times. But if you're using what tends to be a low power on a variable star, that seeing really doesn't have much of an effect at all.
Okay, thank you for that. Trevor Worrell. Trevor, can you unmute?
Yes, I'm unmuted.
Thank you.
It's really an observation that I made. I'd imaged the firework galaxy in 2018 and again recently. And when I do that, I sometimes blink the images together. And I just wonder if I could share my screen, and this might be right down Michael's street, this, and tell me, yeah.
Hold on, I need to just spotlight your video.
Okay.
Can you share your screen now?
Yeah.
Oh, sorry. Is the fireworks galaxy? Is that is the fireworks galaxy? Is that NGC 69 something?
6946.
Yes, that's the one. Yeah.
I'm just trying to share the screen. I've just put a couple of images together,
right,
but I'm seeing a message coming up. Host disabled participants.
Hold on.
Yeah, the reason why I thought it might be that galaxy is that it's traditional for producing supernovae.
Yeah. I don't know if my screen's visible now.
Your
yeah, there we are. And you've got the clustering as well.
Yeah. I just hope that I can flip through the images. I might have to do. That's it. It's just a bit slow. So this is the recent one I took a few weeks ago, and blinked them together. And I've got some more finer detail about this. But when I blink them, hopefully this will play. The star in the middle. I know there's a lot of I've tried to balance both images the best I can, but you can see there's some significant change in that one. Just do it again. I don't know if that's coming through okay.
That's coming through fine.
Right then, so I stop that and go to the next one. So
yes.
Over in the corner there, and when you zoom in, you can see. Obviously, it's a lot dimmer now, and that's basically all that's left. But then I went on to try and find some information, and I used something called Aladdin, which seems to be access to a load of databases.
Oh, yes, Aladdin's wonderful. Yeah.
Anyway, from that, it came up with a location. Is it a 2-mass survey that they did?
Yes. That's they saw the sky in infrared.
That's the only reference I can see there, that J20351 number. But then the trail went dry. I couldn't find. It's obviously something's happened there, but there was no reference to it. And I wondered, as amateurs often find these events, there seems to be not an easy way to put them into the system for those with more, understanding of these things to analyse them. And I just wondered whether you could point me in the right direction to take this a little bit further, because I'm sure it's a known event, but it's just out of curiosity to see what happened to it in those between those 2 years.
Let me. Right, as you can see there, it's very obviously a red star.
Yeah.
Which means it's probably variable for one reason or another. It would be interesting if you took the picture of the same area again, because if it's, say, a supernova, then you wouldn't be seeing it anymore because it's already exploded.
Yeah.
But on the other hand, if it is some sort of pulsating variable, then you might catch it kind of brightening up again.
Yeah.
So it's probably worth taking another picture.
I think I'll probably put it on the list each season and just so it develops. I think it's just pure chance that I caught it at quite a bright point. 2018 was the bright one, and now that's what we're seeing now at the moment. Well, I just thought it's coincidence you were doing your presentation and then caught this thing. But as I say, you ran out of options trying to get a description of what it may be, because it's got a number. So I thought, well, look in a catalogue and see whether it's shown as a variable or some other event that took place. Did you say it had a 2-mass number? It was 2 MASS. Yeah, I think the 2-mass number was that J. Please don't quote me, but I'm sure I ended up working out that it was that, which happens to be its coordinates as well. Right. Okay. If it's 2-mass, that stands for the 2 micron all sky survey, which looked at the sky in infrared light. Infrared is very good for picking up young stars, because what it picks up is the actual sort of gas cloud rather than the star itself. The gas cloud itself isn't bright enough to shine in normal light, but it's bright in infrared. Basically, the number that comes after it is just its position. So it's 20 hours, 35 minutes, etc. Yeah. So that will be the 2-mass catalogue. If you use Aladdin, that's based at the CDS in Strasbourg. They also have a thing called Vizier, VIZIER,
where you can search all of the catalogues. It's got thousands of catalogues there, and it will certainly have the 2 mass catalogue. So you can just put this number in, 2 mass J 2035, etc., and it will come up with details of it.
Okay, Trevor, I muted you because we were getting some feedback.
Yes, there was a bit.
You've got a comment. Would you like to unmute yourself?
Yeah, that's fine. I'll head for that busier side and see whether I can take it a little bit further, but maybe include this in a future session. But it's just quite interesting how it just popped out at the screen, blinking the 2 together over that 2-year period.
Yeah.
Okay, Trevor.
Thank you very much.
Can you stop sharing your screen? Thank you.
Yeah.
It must be fell.
Is that clear?
No.
No.
All right, Gary, you had a comment to make. Read that.
Well, that star that Trevor's looking at, I looked at it up in the software that I use, called the guide, and that comes out as V2192 Cygni. It is a known variable star.
Yes, if you actually looked at his map, that was close to it, but it wasn't the same thing. I did actually notice that.
Yeah, I think the variable was V2192 Cygni, and
Yes.
it was just a couple of degrees away, if that.
Right.
That's as close as I could get, but as I say, got the 2 mass number, but then no other information. It just acknowledged it was that location, and nothing more spectacular than that.
Okay, so well, thank you for that. I think any correspondence, Trevor, I think we'll put you straight in touch with Michael. So you
Yes,
can,
please. Please do, because I can access. I mean, I can access things like sort of VSX, which has got all the latest variable star discoveries in it. But the really interesting thing that struck me when you said you were photographing the, do you call it the fireworks galaxy? My first thought was it's very productive of supernovae, that particular galaxy. And, you know, for one moment, I thought we might have a supernova discovery on our hands there.
I wish.
Okay, Roy Gunson.
I just got a query. We had a talk last week about the sun and sunspots. So, I mean, presumably our sun could be considered a variable star on an 11-year period. I know it only gets very small black spots on its surface, but surely that's going to affect its brightness very, very slightly.
Well,
all stars would be in some way variable in the same way.
It's strange you should say that, because in fact the AAVSO does have a solar section, because, you know, they came to the same conclusion. You know, strictly the sun is a variable star because of the sunspot cycle. And in fact, they have a very active solar section. But yes, I suppose it depends how you want to define a variable star. We are now actually discovering what are called micro variables, you know, which are variables that, yes, they change in brightness, but only by about, you know, a sort of a thousandth of a magnitude or whatever. And probably that's what the sun would be like to, you know, to someone else. Yeah, it would vary, but, you know, not really enough for most people to call it a variable. Okay, technically it might be.
Okay, has anybody got any other questions? No? Well, I think we've covered the ground. Michael, thank you very much for a very informative talk.
That's
I
fine.
didn't realise that variable stars, we included planets revolving around them as well now.
Oh yeah.
That's something new.
That's kind of the cutting edge at the moment.
Right.
Um,
Okay. So-
in there. But I hope you do realise this is only the vanguard of the Norfolk takeover of your society.
Don't worry, we'll stop you at the Trent.
Oh, blast.
So, can we give our usual Mexborough and Swinton thanks, please?